Okay. All right, guys. Here's what we're gonna do today. Two things. On Friday, when we did the voltage drop calculation, we assumed that the load is lump summed in one spot and the source of the power in a completely different spot, and in between them there is a distance. And we did a voltage drop calculation based on this assumption. In reality, some of the loads are not lump summed in one location. You can look above your head. We took an example of the lights scattered all over. So how would we do if the load is not lump summed in one location? A very good example of this, guys, would be parking lot lights or building lights. Building lights in a small room like this is not a big deal because you can see from the panel over here to the furthest distance, probably you're looking at 25, 30, maybe 40 feet. That's okay. But when you get into a parking lot situation, guys, from the panel inside the building to the parking lot, the furthest parking lot light could be, you're talking about 1,000 feet or 1,500 feet. So that becomes a big deal. So let's go ahead and take this example, a parking lot example. And how do we find the calculation for a parking lot example? A lot of people, guys, tell you. So let's take this is voltage drop, and I'm going to say load as voltage drop, load as scattered. Maybe there's another T in it. We have two T's in scattered. We have another one just for you guys. Scattered. When the load is scattered, we're going to find the voltage drop. Let's take the following. Let's take the following scenario. And let's just use, for the ease of installment, use this example that we have. We have a building here, and we have a multiple lights over here. One light, two light, three lights, four lights. Here. And then there you go, and right in here. So here's my parking lot, and in between this parking lot we went and we installed our lighting fixtures. What you're looking at, guys, is the parking lot. We came all the way and we fit it from a 20 amp circuit. We have a 20 amp circuit that moving all the way and feeding these lighting fixtures in a parking lot. Anybody has any issue with that? Seven parking lot lights that we need to feed from this system, 20 amp circuit. The voltage, let's establish the voltage. The voltage is 120 at the source. The voltage at the source is 120. The conductor, when you go into a parking lot, guys, don't you ever start with less than number 10. Don't you even think about it. Don't you think of number 14 or number 12. Minimum, small parking lot, minimum number 10. That's your start because of voltage drop. Then you can go higher than that. Let's see if we design it. Can I, Spencer, can I land the number 10 on the 20 amp circuit breaker? No problem. Why did we oversize the conductor? Because of voltage drop. So the assumption is that my conductor here is, I have three conductors, number 10. Anybody knows why three conductors? Hot, neutral, ground. Hot, neutral, ground. One circuit, hot, neutral, ground, number 10. The lamps that we're using them, these lamps or fixture are rated for 2 amps each. They're rated for 2 amps, 120 volt. All the lamps, all the fixtures in the lamps are rated for 2 amps, 120. Typical, 2 amps, 120. And I'm having 7 lamps, right? 1, 2, 3, 4, 5, 6, 7 lamps. 7 lamps, and I need to find what's the voltage drop at every lamp. at every lamp? What's the voltage drop at every lamp? Any question, guys? Okay, so let's go establish right at this point. There's a 2 amps here. Right at this point, there's a 2 amps here. Right at this point, there's a 2 amps here. There's a 2 amps here, a 2 amps here, and a 2 amps here, and a 2 amps here. You guys agree with me that each one of these, the parking lot cable is coming to an enclosure. You tie number 12 or number 12 probably, or number 10 all the way up to the top of the pole to connect your lights. So we're just looking at the bottom of the pole. That's what we care about most of the time. From here to the top of the pole, guys, you don't have problem with 2 amps. Okay, see where the 2 amps are coming from? Every dot here and circle is actually a pole sitting with a lighting fixture. Let's analyze the circuit. I want somebody smarter than Chad to tell me how much current do you think right at this point, from this all the way to the first light, how much current is going to be this section of the parking lot underground cable is going to see, and why? Look at it. 2, 1, 2, 3, 4, 5, 6, 7. 7 times 2, 14 amps. Anybody does not know why 14 amps? Because the first section is going to see the full complete 14 amps. The first section is going to see the full complete 14 amps. So that's 14 amps. Anybody that have any problem with that? The first section is going to see the amps coming and feeding every single one of these fixtures, right? The first section. What is the first section? From here all the way up to here. Let's draw some distances, guys. The distances that they're giving us, they have a 25 feet distance from here to here. From here to here, they have 75 distance. And to here, they are giving us 100, just to make it easier, 100. And from here all the way to here, right? We're given 100 feet all the way to this point, and in between each two, I have 100, and just for the sake of ease of installation, 100 feet, and from here all the way to here also 100 feet. And what do you expect from here to here? 100. Now, in reality, most of the time, you guys when you lay out your parking lot lights, you want them symmetrical. So that's not bad of an assumption. You want them symmetrical, meaning the distance between them is equal. That's how we run our parking lot lights. Okay, everybody see what the scenario is? I have a 20 amp circuit feeding 7 lights. Each one of them is 2 amps, 120 rated lamps, and the distances are indicated in green color. Basically 100 feet between the fixtures, 100 feet between the fixtures. Okay, anybody has any problem with the assumptions first? The assumptions. And what do we need to do? We need to find the voltage drop at every fixture, Okay, so I need somebody to tell me what would the current right at this point be. Let's count. 1, 2, 3, 4, 5, 6 times 2, 12. Right? Why? We don't count this one because that light took its current and she's happy. So that's 12 amps. Let's go back and see the current right at this point. What do you guys think the current at this point? 10 amps. All right. Let's go and see what the current at this point. Right here, look at that. Current at this point. Coming and feeding what? 4 amps. Everybody can see that, guys? How about the current at this amps? Right here. This is 4 amp too. How about the current here? 2 amps. How about the current? Where's the current? The current right at this point here. 2 amps. Can you guys see how the current is distributed through these network? Everybody knows why 2, 4, 6, 10, 12, and 14. Any question so far? So now we're gonna take the voltage drop at every pole. So when I ask you, Brad, what's the current right at this point? 14 amps, right? Because that point, as the cable comes and emerge and feed this fixture, it's going to see 14 amps going through that feeder. 14 amps going through it. Here's what it looks like. So as the cable comes from here and go down to the next fixture, and then go up, here's my 2 amps going up. But the feeder itself, right at this point, guys, has how many? 14 amps, right at this point. Right? This is the enclosure. Feeder coming in, you tie, and you go up to the fixture. Your fixture will be located right at the top here, with 2 amps going right into it. 2 amps going right into it. Okay, we're going to do the calculation, the following calculation. Mark your stuff over here. We're going to do the calculation number 1. We're going to do calculation number 1, number 2, number 3, number 4, number 5, number 6, number 7. We're going to do a voltage drop calculation at 7 points. And each one of these points, guys, has to meet the 3% voltage drop criteria. The 3% voltage drop criteria. Okay? Any question, guys, about the assumption? Any question about the assumption? Now, you could do the same assumption, guys. Look how easy. If I find that, which one do you think it's the worst scenario? Which one the worst scenario? The last one. So it could be that, because from here to here is 200, and also from here to here is 200. These two could be the worst scenario, meaning they might encounter the lowest amount of voltage drop. The lowest amount of voltage drop. Now, if I end up with a voltage drop right here at 7, more than 3%, what do? You go back to number 10 and up it to number 8 and do the calculation again.
It would be the lowest, it would be the highest voltage drop on it.
Yeah, the highest voltage drop, the lowest operating voltage. That's what I meant to say. Thank you. The lowest operating voltage you're going to encounter here, which means the highest voltage drop is the furthest distance. Makes sense? Mr. Irbab?
10.
10 points. Any question, my friend? No? Cool. This is parking lot voltage drop calculation, guys, very common. You'll be doing it all the time. Okay. So let's so everybody knows what the assumption is. I'm going to repeat with you. When we do the calculation, we're going to find voltage drop. At point 1, I'm going to use RIL, R-I-L over, it's single phase, 2 RIL, 2 times RIL, R-I-L over 1,000. So R, then I'm going to pick R for number 10 from the table. I at this point is what? 14. And L at this point, from here up to this point, is what? 25 plus 75 is what? 100. And what is L? We got L, we got I, we got R, we got 1,000. So basically that's it. And then we find the voltage drop at point 1.
So what is it?
We're gonna be working on it. And then when we go to 2, we're gonna go take the distance from here to here. 2, we're gonna take the distance from here another 100 at 12 amps and so forth. Okay, let's go ahead. And any question, guys, before I move to number 1? You'll see how it becomes very easy as we start going through it. Let's go number 1. I want you to remember that number 1. Okay, let's go do the calculation. I want to say number 1. Number 1, at point 1, voltage drop equal to R-I-L over 1,000 equal to times, what's R for number 10? Is it 2? 1.2? Yeah, 1.2? 1.24? Did you get it from, yeah, not from... Stranded.
Yeah, 1.24.
1.24, okay. This is from the NEC code book.
Where did that come from?
Let's go. I'll spell it, and then I. What's I at this? The first section up to 1.
14.
What? L. 14. Thank you. And what's L? 100. And what's the 1,000? 1,000, Chad. Duh. Okay, now to answer my friend DJ who wants 100 out of 100 and the participation, this point here came from where? Chapter 9, table number 8, number 10, stranded. Stranded. As close as stranded as you can get. Okay? The rest of them is just right in the formula. I need a guy who's going to get 10 out of 10 in the participation to answer it.
3.47.
Right? 3.47 volt. I need another gentleman to agree with that, other than DJ.
Billion.
That's right.
Good? Yep. Volt.
You didn't say lady.
Oh, I'm sorry, or lady. Oh, I keep forgetting. Oh,
You should get a 10 in there.
oh, or lady. Now, is this good, bad, or ugly? Is this good, bad, or ugly? Not Scott. Not Scott. Stop here. The voltage drop. 3.47. How can I tell if it's good, bad, or ugly at this point?
Be 3 at least.
Right?
Or less.
I can't. But I can't. How do you know? You need to go back to find the voltage drop percentage. Then we find voltage drop percentage equal the voltage drop divided by voltage, right? Here's how we find the voltage drop percentage. Voltage drop divided by the nominal voltage of a system. So you have 3.47 divided by mother voltage, 120. What would that give you guys? How much?
2.89. It
2.028.
would be,
Point 028.
yeah, 0.208.
Points
Three
in
point
percentage.
Zero. It's 2.9%.
2.9%.
Bad.
2.9%. Now this is up to this point we're cool. We don't have a problem with that one. Up to this point, guys, we're cool, right? We don't have any problem with that. We lost, but how much volt we lost so far? Look at the voltage that we lost. 3.47, just in this first 100. We lost 3.47 volts. I want you guys to keep track of that, how much voltage we lose. Okay, let's go to 2 when you guys are ready. It's gonna, Spencer, the nice thing, it's gonna be repeating itself. Exactly like Easter and Christmas and all these things keeps repeating itself.
I'm trying to find that 1.24.
1.24 is for number 10, stranded. Number 10, conductor number 10, stranded
They
here.
kill a feet.
And
I was going under the wrong.
there you go. Unquoted 1.24. Makes sense?
Yeah, I just didn't see that encoded.
That's okay. When we have copper, guys, the assumption from chapter 9, table 8 is always copper, always unquoted, unless you know otherwise. Any question, guys? Should I move to the second one? Ryan, my friend, we're cool. Okay, let's go to number 2. Number 2, I need somebody to help me because you guys have the graph. Voltage at number 2, voltage drop equal 2 times at number 2. At number 2, what was the amp at number, the R still the same, right? R still 1.24 times rel I. What was the I at number 2? 12 amps. 12 amps. What's the distance from only from number 1 to number 2? Only from number 1 to number 2? 100 feet. Now mistake number 1 is you take the distance from number 2 all the way to the building. No, just between 1 and 2. We're looking at this segment of the process. Camille, my friend, right between light number 1 and light number 2. It's 100 feet. Divided by 1,000. Why do you divide by 1,000? Because the table gives everything in kilofoot. Yes, sir.
What if you were to want to do this equation number 2, but you wanted to include number 1?
Do you have 2 different amps? You can't include the distance number because here's when I ask you, if you go all the way to the building, I want to ask you, what's your amp? 12? No, because at one section the amp were 12, at another section the amp were 14. Very good point. Why do I have to sectionalize it? Because at one section the amp were 12, at another different section the amp went up because we get closer and we pick more lights. Does that make sense? Yeah, that's why I can't use it. You're inching towards your 10, man. Any question, guys? A lady or a gentleman? 2.98 volt. Is this good, bad, or ugly? I don't know. Voltage drop equal 2.98 divided by the source voltage. By the source voltage, 2.5 at 120. What would that give you? How much? 2.5%. 2.5%. Actually, guys, do you agree with me? What's the voltage at 1 though? What's the voltage when you reach 1? Let's go back one more here. 2.98. 2.98. I lost 3.47 here in the one section, and in another section, how much volt did I lose? Another 2.9. So I want you, can you guys, I want to put question mark next to this. We'll get back to it. Okay, just put question mark for the time being. Is my assumption right that 2.9 divided by 120? Is this how much voltages I really lost at number 2, or did I lose more voltages at number 2? Did I lose more voltage at number 2? Why? Because remember, we lost 2 point something up to 1. That's already lost. And then as we reach 2, we lost another section. So put question mark next to this.
So would you just put the total voltage of the other one instead of 120? 120 minus.
Let's just put. Can you guys just keep a question mark, and let's go calculate 3. Calculate 3.
2.48.
3.
2.48.
Voltage drop equal 2 times, what's the R? 1.24 times, what's I for 3? 10? 10 times, what's the distance for 3? Between 3 and 2? 100. Divide by 100. Plus 0. And that will get you 2.48. 2.48. Anybody disagree? Yes, no? I need another gentleman too.
That's right.
That's right? Okay. All right. I'm going to do number 4. We'll find the voltage drop later. I'm going to do number 4. Number 4, the same thing. Voltage drop equal at number 4. 2 times 1.24 times. What's the amp at number 4? 8. 8 times 100 divided by 1,000.
1.94.
How much?
1.94.
Yeah, it's 4 amps.
Oh.
4 amps. Subtract 2 from your approximation, DJ. 4 amps. Okay, what's the answer?
Yeah.
0.992. 0.99 volt. Okay, let's do number 5. Number 5, voltage drop equal 2 times 1.24 times. What's the current? What's the current? 2 times. What's the distance? Is it still 100? And divide by 1,000 equal 0.496.5. How about 0.5? 0.5? 0.5 volt. 0.5 volt. And let's make this one, guys, just for the sake of argument here. It's almost 9991. 1 volt. 1 volt and 0.5 volt. Okay. We have 2 more points and then we're done. 2 more points. We'll do the calculation for them. Two more points. Shall we do it? Okay. Number 6. As voltage drop equal 2 times 1.24 times, what's the amp? 4 times 100 divide by 1,000 equal. We did this, didn't we? What is it? 1 volt. How about 7 and then call it a day? Voltage drop equal 2 times 1.24 times 2 this time, times 0 divided by 1,000 equal 0.5, right? 0.5. Okay. So we found the voltage drop, how much voltage drop at every light we're going to lose. Now I want you guys to remember these numbers. We're going to start counting how much voltage is actual volt we lost at every point. Questions before I go to my graphic? Go back to my graphic. The graphic that we did. Okay. Go back. I want you guys to give me the. Now let's go count the volts. I want to count the volts in green. I want somebody at point 1 count all the volts that we lost at point 1. Count all the volts that we lost at point 1. At point 1, I'm going to erase this. Where's the one? This is at point 1. Count all the voltage that we lost at point 1. Do you guys agree with me? The only voltage that we lost at point 1 is 3.47, right? We didn't lose anything else. So check. This calculation then is okay. 2.97 is okay, right? Because it's divided by the voltage, the 120 that we started with. So that's good. Let's go to number 2. Number 2, let's keep this one. I want you to add all the voltage that we dropped. So voltage drop equal voltage drop. This is the voltage drop equal voltage drop 1 plus voltage drop 2 equal. What's voltage drop 1 and 2, guys?
6.45.
The first one was it? 2.3.
3.9 or 3.
The first one was 3.47 and then
3.47 plus 2.98 equal 6.45. 6.45. Okay, now this is how much actual voltage we lost at number 2, not the 2.98, guys, right? Because we already lost it. See, can you guys see that? We already lost the stuff. So instead of having this number here, I want to go and put 6.45. And what's the percentage from the source voltage? 5%? 5.3%. 5.3%. 5.3%. No good. Can you guys see why? Because we lost a lot of voltages as we lost a lot of voltage from the 120, 5.3%. What does that mean? We exceeded the voltage calculation at this point. What do we need to do? Up the wire. 5.3%. But we know we have a problem right now, but let's just go find the voltage drop for all of them. Okay, any question, guys? Why did we put 4.45 instead of 2.98? Because we're moving further and we're adding how much volt we lost at every station. Okay? Let's go to 3.
Can't you just add them all together and calculate it for the first one?
No. The distances are different. They're scattered.
Well, if you know the voltage drop on each particular light.
Yeah, you can, that's what we're doing. We're adding them. Let's find the voltage drop, guys. Voltage drop right here equal voltage drop 1 plus voltage drop 2 plus voltage drop 3 equal. I want you guys to give me, if you don't mind, the 2, 3, the 1 and 2. Was it 3.47 plus 2.98 plus 2.48 equal
8.93.
how much?
8.93.
8.93 volts. Now, are we still going through the loop, right? All right, now the voltage drop percentage equals 8.93 divided by 120 that we started with. What would you get?
7.4.
7.4%. 7.4%. 7.4%. Okay, let's see where for. Are we still going through the same loop? Are we still going through the same loop? When did we switch? We switched. So let's go. Any question, guys? We just added how much volts we lost through the stages. All right, I'm going to go back to. I'm going to move my 1 volt somewhere, so I can't have enough room. You guys don't have that luxury. 1 volt, and I'm going to have voltage drop 4 equal voltage drop 1 plus voltage drop 2 plus voltage drop 3, right? Plus voltage drop at 4, right? All these voltages, right? Are we still around the? Yes, sir.
I have an odd question.
Yeah.
The voltage drop, if we were calculating number 2, did we ever minus the voltage that we lost?
You can do that to find the operating voltage. So if I ask you what's the operating voltage at 3, you subtract all the voltages that we lost at 3 from 120, that'll get you the operating voltage at 3. And that's what we're doing, right? The operating. Subtract all the stuff that you lost at 3, 2, and 1. From 120, that'll get you the operating voltage at 3.
Right.
All right, what's this one, guys? I'm going to keep, since we're carrying it over, I'm going to say this is 8. All these together were 8.93 plus the rest, which is 2.48. What would that give you? 10, 11, 11 point? No?
You're adding 1. The voltage drop at 1 is 1. The voltage drop at 4 is 1.
It's 1.
Oh, the voltage drop at 4 is 1. Okay, where's the point?
8.93 is 1 through 3 plus 1 is going to be.
Ah, thank you. Thank you, thank you, thank you. Voltage drop 1 plus voltage drop 2 plus voltage drop 3 plus voltage drop 4. And these all 3 together, they made 8.93 plus 1 equal 9.93 volts. Anybody disagree with Chad? Because the first 3 we already calculated them. So let's find the voltage drop percentage. Voltage drop percentage equal 9.93 divided by 120 equal 8.3 percentage. Good, bad, or ugly? Ugly. %. See how we added all the voltages as we moved through, added all the voltages. Okay, now this is one which we went this way. Now we're going to go all the way to number 5. Number 5. Any question, guys? Any question? As we add these voltages. Everybody got the rhythm of what we're doing? We're adding voltages and dividing them by the source voltage. Adding voltages, dividing them by the source voltage. Number 6. I'm going to move mine here 1 volt to here, so I can have room. You guys don't,
0.5.
you guys don't have this luxury. So voltage drop at 5 equal voltage drop 1 plus voltage drop 2 plus voltage drop 3 plus voltage drop 4, right? Do we add 5 too? Is it going through 5? No, it's going, it's at the end. 6, this is number 6.
6 is not going through 4, 5.
It's not going to 4 because yeah, we went the other way. So we have 1, 2, 3, and then we split, right? 1, 2, 3, we split. 4 and 5, we calculated them. That's it. And then this is number 6. Voltage drop number 6. 1, 2, 3 plus voltage drop at 6. Everybody knows why we skipped the 5 and 4 and 5, because that's a whole completely different branch. They didn't go through it. The current did not go to 4 and 5. It's a completely different branch. Okay, how much? You guys remember what were these two together? 3?
The 3 of them,
What was the 3 of them together?
8.93.
Is it 8.93 plus 1 equal 9.93 volt, right? I want somebody to, right? 8.93. And if you do the math, the same math that we did, that will give me 9.93 divided by 120 equal voltage drop. Oh, what did we say we came up with here?
0.5 is
We added 1. What did we come up with? Brad, Holly?
8.3,
We have
983 divided by.
yeah, 8.3, 8.3%. 8.3%. The last section, guys. Did we do anything wrong here? Anybody? We add them up? Yes, sir.
The one that you're adding on to 0.8 or 8.93, was that the
first 3.
from number 4?
That was from number 6.
Oh, okay.
Number 4, because number 4 is a different branch.
I got it.
It didn't go through it.
Number 24.
Okay, number 7. Voltage drop for number 7, guys, equal voltage drop 1 plus voltage drop 2 plus voltage drop 3. Now, we split. At 3, we split. It went through 6, though. Plus voltage drop number 6 plus voltage drop number 7. Equal. So up to this, all these we found it, right? 9.93 plus number 7 as 0.5. That'll give me 10 something. 10.43 volt. And to find the percentage wise, voltage drop percentage equal 10.47 divided by 120. What's the percentage, guys? How much?
8.7.
8.7%.
10.43 or 10.47?
10.43. Thank you. 10.43. 10.43. Thanks. We didn't do the calculation for 5. That's why I was confused. We'll do the calculation for 5, guys. But by the way, 5, the same calculation as a 7. Same calculation as number 7. And what was the voltage drop at this point? The percentage. Voltage drop percentage 8.7%. Yeah. Right? 5 and 7, guys, are the same distance from the circuit. So the same calculation would apply to them. Same as number 5. That's what I thought. I jumped in 5. We dropped 5. So the same calculation as in 7. 7 and 5, 4 and 6 are the same points, distance-wise, and the same characteristics, the same current, so they will be the same value. Any question, guys? Any question? Now, obviously, this is not an acceptable voltage drop. Yes, sir. Camille?
Oh,
No? Any question, guys? Two things you get out of this example. Number one is never use number 10 in a parking lot that large. Number two is never use 120 voltage in a parking lot that like that 120. 120 is a voltage, the least productive voltage system that you can use. Use it inside. When we do parking lot, guys, most of the time either you burn these equipment at 480, if the voltage system is 480, the ballast is powered at 480. If you do a 480, imagine that give you close to 4 to 5 times more voltage, powerful voltage, 4 to 5 times more powerful voltage to push further distances. Or you can use 277, and some application they use 600 volts and burn the equipment to 600 volt. So, but if you are in a parking lot where the only available voltage is 120, you might have to consider, because these are, if it's commercial, it's coming from 208, 120, Spencer. You might have to consider using 208 voltage, actual 208 voltage to push it distances. If you are stuck with 120 just because your grandma said so, and she doesn't want to change her mind on her parking lot, then you have to up your conductors. A lot of engineers, commercial guys, we start with 4-aught when we do parking lot. 4-aught conductor. You go for 4-aught and the voltage 480 or 277, and you push your voltage further distances. Look how many 100 feet. What was the longest distance was 100, 100, 300, 400, 500 feet. 500 feet is a long distance. So a lot of people use 4-aught, 2-aught, 1-aught conductors when they power the parking lot, not because of the amount of power, it's because of voltage drop. Expensive is do you need your system to work efficiently? But if you want to, if we're to redo this system, which do it as an exercise, then I would start with number 8, number 6 conductor. I would use number 6 right away. Number 6, because the voltage drop looks like number 6. Put number 6 and do the same calculation. Your goal, Spencer, is always to end up at every fixture of what? 3% or less. Because we're assuming these are feeders and we're tapping them to feed all this from the source, the voltage drop all the way down. We're assuming these are feeder, we're tapping them 3%. You don't want the voltage drop at each fixture to be less than 3%. That will get you a well-functioning operating lighting system. Any question, guys? See how easy that is? No? Is it hard? Adding the volts? What was the furthest one? We said, was it 5.8 one? For this calculation, our furthest calculation end up with voltage. No, not this one. So go back. There you go. Furthest calculation end up with 10 volts. Right, very similar to what they came up with, 10 volts. Any question, guys? Any question about that? That's it. That's parking lot. We will do as we go. We're residential. We use 120. And next project, we will do a couple of examples, guys, next quarter with using a 277 and 480 calculation. Same principle. Same principle. Now, where's DJ? DJ, my friend, before I give you a break here, this calculator is not capable of doing this type of scattered load. Electrical Calc Pro, you have to do it. You can do it, but you have to use it basically 7 problems to come up with a solution. So you can't just click a couple of buttons and get the voltage drop at every single fixture right from it. This assumes that the load is lump summed in one location, the source in a different, and in between them a certain distance. Voltage drop for other applications, as like motors. Yeah. These are great for motors, for loads that it's not scattered, lump sum. Any question, guys, about this example? When you come back, that's the only example I want to do about this. It's really all of them. It keeps repeating itself. I want to do an example about fire pump starting capability of a fire pump. Voltage drop at the start of a fire pump, and then we'll call it a fire. We'll call it voltage drop quit for the day, and then we'll do advising.
Yeah.